Hello, everyone. We will now be moving into our next session from Cumberland Additive on exploring technical aspects of AM for oil and gas qualification and production. Brenna is an additive manufacturer working to qualify AM parts for aerospace and oil and gas. She recently earned her master's degree in additive manufacturing and design and acts as the ambassador for the Austin chapter of Women in 3D Printing. Nick Bass is an additive manufacturing engineer at Cumberland. He spent 8 years with Lockheed Martin working on space and defense projects and system-level mechanical and environmental testing. Upon his departure from Lockheed, Nick joined Flex and began working in high-volume manufacturing environment, factory assembly lines as tooling. Since joining Cumberland, these parts in industrialized AM processes and applications. Nick brings a decade of high-tech, high-volume, diverse industrial experience to advance AM applications and process to mirror that of mature, high-volume tech industries. Thank you both for joining.
Thank you.
Thank you.
And if you would like to share your screen as well, there's a button at the bottom. Perfect.
Alrighty.
Signing off.
Thank you. So thank you everyone for joining. I know it's a little bit late for some of you, so I appreciate you taking the time. So yeah, we're going to be talking about qualification and production of AM parts for oil and gas, and some of the technical considerations that go along with that. Something I want to note right off the bat, this is not intended to be an all-encompassing presentation. We want this to be kind of a jumping off point for further discussion. So I encourage you to stick around for the Q&A or come talk to us at our table 509 or reach out to myself, Nick, or anyone from the Cumberland team. So there we go. And right off the bat, I want to talk about just the technology a little bit. Obviously, we're all here to talk about AM, but we're going to be talking mostly with powder bed fusion, particularly laser powder bed. So the important thing to note about laser powder bed is the process by which a layer of powder is deposited onto the powder bed and then selectively welded by the laser to build your 2D layer, which then creates your 3D part. Laser powder bed parts are considered more net than near net. There's no binder involved that you need to burn out. There's no sintering at all. The parts are fully melted right out of the machine, and you get parts that are 99% plus dense. So you could really print a part, pull it out of the machine, and be ready to go. A little bit of an intro to us. The Cumberland site, just north of Austin, Texas, was founded in 2006. We specialize in metal and plastic AM parts. We support customized for aerospace, defense, space, and of course, oil and gas. We have 17 powder bed fusion systems on site using both laser and electron beam powder bed, making both metals and plastics. So let's talk a little bit about qualification. Qualification is basically just your process of validating the process. It kind of falls into 3 categories. You have process, part, and production. So process qualification, this is your idea that you test everything right off the bat to obviously validate the process. This is not part specific. You're basically testing all of your inputs so that once you get the properties that you want, you lock in your process. The good thing about this is if you're working with an experienced manufacturer or if you've been printing a long time, there's typically a lot of data behind established processes. So obviously if that's acceptable to the customer, you can piggyback that data and avoid high testing costs and a lot of time associated with establishing those statistical data sets. Separate from that, you have a part qualification. Part qualifications are used if you need to test the part before you go into production. So with process qualification, you typically have a build of test specimens. With the part qualification, you're building the actual part and testing that. Typically, you're doing some sort of destructive testing to it. So this is commonly used if you need to expose the part to a specific environment, or you need to cut it up and look at it for any reason. So those are your qualifications. The most commonly used type of validation is just through production testing. This is typically used in conjunction with a part qualification or on its own. And this is the idea that you just add whatever test specimens you want to the build itself. So you're making your part for production, and you're sending test coupons along with it. That way you have, at the end, when your part is done, you have a representative sample of the metal that was printed, and a good indicator of how that part will perform. This is the most important step for risk reduction, as it's really your proof of performance on a build-to-build basis. So we're talking about this qualification, fixing your process. What does that actually mean? And what do you have to define? So here we have kind of our list of what we commonly see as being fixed in a fixed process. And the idea here is that you want to clearly define your inputs, and you wanted to define the data that you need to get. So that way you know exactly what's going in, you know what's coming out, you can validate that you're getting repeatable quality with each part. That's really the name of the game. It's making sure you're getting the same part, the same properties that you want every single time. Something to note here, I know this looks like a lot. It really depends on your application, what from this suite of things you want to do, but all of these can be done with your part print. None of these require a standalone qualification. So yeah. So let's talk a little bit about standards. Historically, we've seen design authorities making their own specifications for procuring AM parts. However, in the past few years, we've seen standards organizations start to create their own. Here's just a list of the kind of common ones that we've taken a look through. These are really going to establish your guidelines for qualification as classified by part criticality. Typically, you have highly critical, lesser critical, and non-critical. And with each of those classifications, you have different levels of testing rigor. Usually, you're going to have more critical parts, needing more testing, leading to a higher testing cost. So really, the benefit here is obviously you don't have to write your own spec, and adhering to these standards really standardizes the process, obviously, and helps you avoid the what-ifs that can come up when working through the production process. So whether you're making the switch from traditional manufacturing to AM, or you're designing a part right off the bat, you need to know what properties you're going to get. Nickel alloys 718, 625 are incredibly common in oil and gas. So we print a lot of 718, so that's what we'll be focusing on. And here we have some data of properties that we get by our process at Cumberland, plotted with the limits set by API and AMS. So as you can see, we really don't have any problem meeting those mechanical properties. So when we're talking about switching from traditional to AM manufacturing, we materials kind of into high readiness and more difficult. Your high readiness alloys are going to be the ones that AM is already good at. They're ones that have a defined process, machine manufacturers are familiar with, materials readily available, stuff that has a low barrier to entry if you want to start printing this material. And then obviously there's some materials that don't really transfer that easily to AM. These are your more difficult materials, something like your 6000 and 7000 series aluminums. They might be a commodity in machining, but they are prone to cracking with laser powder bed fusion. So it's going to take a little bit of work from our dear metallurgists to make that more readily printable. So with that, I'll send it off to Nick.
Thank you, Brenna. So I'm going to start this section of the presentation by going through some data and just talking about some things to consider when looking at oil and gas qualification in regards to these data sets. So we talked a little bit about part-specific qualification and in wanting to consider a specific application for a part. In oil and gas, something that might fall into that would be corrosion. So here's an example of some test specimens after they've been exposed to a corrosive environment at elevated temperature that Cumberland has done. So we tested a bunch of samples at a bunch of different environments at a range of temperatures and found that across all the specimens, the AM material, this is 718, was outperforming the raw material that was purchased as a commodity. In this example, 45C, you can see that the rot has large pits all over, and when we're weighing the samples, there's weight loss. The obvious loss of material from corrosion, whereas the AM material had either negligible weight loss, very little, or just and maybe some corrosion starting to happen at the corners. We've also similarly, we've also tested slow strain rate in a sour environment with similar results. So how consistent are your properties over time in AM? So here's an example where we were tracking tensile properties. So yield, and this what's plotted here is just yield strength and ultimate tensile strength over a year. And you can see there's a little bit of scatter. Most of what at first glance, it looks like there's more scatter than there really is. Keep in mind, there's vertical and horizontal bars, and the horizontal bars always outperform the vertical by just a little bit. So there's a little bit of anisotropy, but it's not a massive amount like you might see in some manufacturing techniques. Scatter is pretty consistent over the course of the year. And this is through multiple machines and multiple powder lots and a whole bunch of builds. What we see in our data is that other properties follow the same trends, especially in a material like 718. Now, this is not always going to be the case, and what we kind of owe this consistency to process controls in place at the factory. What about a little bit more look at a variation between machines? So this is a comparison of two different machine models. In other words, machines made by two different manufacturers. So not even just two machines of the same model. This is two totally different manufacturers. And with that, two different laser parameter sets. Now these are well-developed laser parameter sets that have undergone a lot of testing by Cumberland, and we've settled in and found that, okay, this works. And what kind of consistency can we see across those two platforms that we've developed with two different powder lots? And this is just 4 builds. And this is fatigue, obviously. You can see there's really no obvious difference between the two machines in these sets of builds. So we're seeing good consistency even across our machines that have been well vetted. Now, what I just showed you is the tip of the iceberg. Here's a laundry list of material properties that have been characterized across multiple materials and multiple machines. And these are all things you could consider looking at as part of a process qualification. Now, you don't have to look at all of these things. Maybe your application isn't susceptible to creep. Maybe you're not looking at fatigue failures. So maybe or bearing stress is another one that can be a somewhat specialized test. Now, we've gone through that work already, but you don't necessarily need to for every application. It should be used on a case-by-case basis unless you're just going to throw the book at it. And maybe you can get that data if you're working with a service that's already gone through that. cost and time. Now, I've just been talking about destructive testing, but in this presentation, we'll be talking quite a bit about non-destructive as well. And so here's a short list of those, but we'll go into more depth. Now, in the bottom there, that's an example layout of a qualification build that's gotten repeated a whole bunch of times. So these aren't necessarily builds of just a couple little bars. It's fully dense, or a fairly dense build plate with a whole bunch of stuff on it. So next I'm going to talk about heat treatment. And this is meant to be, again, not really a full guide to the whole idea of heat treatment. It's a little bit of lessons learned from Cumberland and a lot of just ways to get the conversation started, get people thinking. So a little bit of guidance on heat treatment. So the steps that you want to go through, like HIP, solution, age, or harden, whatever you want to call it, is alloy dependent and use dependent. So not every application is going to use the same set of post-build heat treatments. In some cases, no heat treatment is needed. In the case of especially an electron beam powder bed fusion, you don't even need a stress relief cycle. Out of the machine might be good enough. Now, stress relief is typically used in all laser powder bed applications, but even that can get skipped for, it's more of a geometry specific application. In oil and gas, we probably always see at least a stress relief for laser-based processes. On the right, I've got a plot that's showing yield strength and ultimate tensile strength of an as-printed set of specimens and a set of specimens that have gone through a solution in age. You can see there's a massive increase in strength associated with that. So we don't meet API guidelines without that thermal treatment. So when selecting a heat treatment, it's a good idea to consider asking yourself or asking the people you're working with, what data do we already have in order to reduce the amount of testing? And what cycles are standard? That could be standard for an outside processor, a vendor that's doing heat treatments for you, or that can be standard for the group of people that already might have a body of data. So if you can tack your group of parts onto a coach cycle at a vendor, that might really help you out. Now, I find that oil and gas doesn't have as much of a problem with this as some other industries. There's more well-established post-build thermal treatments that have been historically applied to, like castings as an example, that can probably get used for AM as well. Okay, what about HIP? So in powder bed fusion, you're getting a part that's greater than 99% dense right out of the machine in a well-controlled process. But even then, there's going to be some little teeny tiny voids, and running HIP can enhance fatigue life. So really the purpose with powder bed fusion and HIP is to enhance fatigue life. There's no significant shrink that happens through this process because the amount of density that's healed is low. So it's just something to think about. We're not looking at a sponge that then gets shrunk down by HIP. Unfortunately, I think my figure there is not high enough resolution to hardly see it. But if you look real carefully, you'll see some little yellow splotches. Those splotches are voids that are identified in a CT scan image that we're depicting before and after HIP. And in this case, we were able to show that those voids that existed pre-HIP disappear after HIP. You can only even find those things by using a really high resolution CT scan. And this is a tiny sample. The diameter is 3 millimeters, an 1/8 of an inch. And the voids are all healed there. Sorry, the presentation's jumping around a little bit. Okay, so now we'll talk more in depth at non-destructive testing like that CT scan. So common NDT methods seen, this isn't just AM for all kinds of metal parts, are dye penetrant inspection, so LPI, FPI, Dye penetrant, you can get useful data out of that for AM parts, but you should expect a lot of false indications. So things are going to glow that aren't actually a problem. So the image on the right is a dye penetrant where all the glowing, colorful bits are false indications or things that were later deemed not a problem. So that big glob is a surface roughness spot of somewhere in the range of 250 or 500 RA, and because that's an as printed surface. Now, if this part was machined, it would appear in an FPI just like any other machined part. But this part hasn't had a extensive surface finishing, and so as a result, you get these indications that are showing up in the surface roughness. So volumetric is the other kind of major category of NDT that's commonly used in AM. So that's ultrasonic, CT, X-ray. The types of defects you'd be looking for are really, really small. So on the order of not tenths of an inch, but hundredths of an inch. The worst case is an image on the right there where we found an indication of 56 thousandths of an inch. That's, in my book, really, really bad for us. And yet it was being compared against a spec that was looking for 1/4 inch voids. So really, really nasty voids that you might get in certain casting processes. So if your spec is looking for something of that general scale, maybe you just skip volumetric. Yeah. So HIP can heal all these things unless they're surface connected. If the pore goes to your surface, then HIP won't do anything for you. Another consideration with volumetric NDT is that if the wall thickness is greater than about 1/4 inch with 718, something fairly dense like 718, it gets really hard to see through that thick of a wall. And then also complex geometry that AM does a really good job with can also be hard to CT or X-ray because of shadows and reflecting that can happen. So I realize we kind of ran through a really big topic with just a handful of bullets, but again, this is hopefully a way for us to get the conversation started and understand what people should be looking for when thinking about qualification of AM. I think the technology is ready. I mean, oil and gas is an industry that's a late adopter of this technology, but even that industry, we've been supplying with parts for greater than 10 years. The pathfinding for the more stringent qualifications has already been done by multiple other industries, medical, aerospace, and oil and gas is kind of following along that same path now. There's no single right answer here. It's going to be application and company specific. Look at risk, decide what you need to know. Qualification can be a really good thing because it builds trust with the technology and new suppliers that are being brought on board. And there might be some cost and time associated with the process up front. It'll really pay dividends in terms of money in the long term through reduced risk and again, that trust with the supplier. You can throw something on a short lead time if you've already done the testing. But it might expose suppliers that really aren't ready. If a supplier hasn't gone through this kind of rigor and is then trying to work their way through a qualification process, it might stumble. All right, that's all we've got for this presentation.
Thank you, Brenna and Nicholas. We do have a few questions on the Q&A, so I'll get started with the most voted question. You noted completing a gap analysis to DNVGL's qualification requirements. Is Cumberland leveraging certification bodies like DNVGL to support your qualification programs for oil and gas?
Yeah, I'll take this one. That's been a project I've been working on. So yes, so we're working with multiple customers right now who want to use the DNVGL spec. So that spec is just coming out. It's a really great effort by that governing body. Great presentation earlier, guys. So right now we're at the stage of doing gap analysis, understanding what's in the spec, and seeing if there's anything that we can't do. And I'll just say off the cuff, there's nothing in there that makes me nervous. We can do that, and that's generally the case with these specifications. They have a lot in common across multiple industries, and it's just a matter of putting it in the right font.
Nick. Next question. Repeatability is tested on S basis, A basis, B basis. What if the need is just for 5 samples?
So the way I'd answer that is the answer we all love to hate. It's going to depend. We're defining our repeatability based on customer need. So if you're only needing to test 5 parts, you want to do 5 consecutive builds to test those properties, that's what we'll do. So repeatability, we're just defining as our knowledge of the process and our ability to maintain properties over a time frame of, for example, a year. But how that's defined for the customers, we'll do whatever you need.
Brenna. Next question. How do you consider the thermal variation of a part within the certification process for validation using mechanical testing?
I'll try to answer that. So if your part has, okay, I'm thinking this is going towards the concept of the thermal history of a part being important. And if there's a great amount of variation within a build, does the specimen on the left side of the plate or at the 1-inch height of the build correspond to something somewhere else on the build? And that's an excellent question. If there's a couple of ways we can approach that. In some cases, we're building integral samples that are placed next to the critical feature of the part and are of a size similar to the feature there's a concern about. Another one can be specialized specimens. Let's say there's thin walls, maybe we put thin wall specimens of whatever kind, that form factor as part of the part qualification or part of the witness on the plate to go along with the build. I hope I answered your question. I'm not totally sure I did.
Sounds great, thanks. I think one last question for you guys. Are there unique qualification requirements for oil and gas, like aerospace has? What guidelines govern the qualification in the oil and gas industry? Yeah,
so that's a tough question right now because there really isn't that much yet. The DNVGL spec that we just mentioned is probably the best or most prominent example that's happening right now, where a governing body is trying to step in and say, here is a standard that you can use across companies for energy. As far as unique requirements, one requirement that comes up in energy that might not come up as much in something like aerospace is corrosion or sour service, and there's others, but it's the demands of the material in oil and gas application might just be a little tweaked from what something like aerospace needs.
Well, thank you, Brenna and Nicholas, both so much for joining us today. And there's a few questions left. I will send them to you after as well.
Great.
Thank you.